Welcome back. In this video, we are going to continue our discussion on important concepts on statistics for interviews on data science. In the previous video, we have discussed on 10 topics. In this video, we continue from topic number 11, bias-variance trade-off. What is bias actually? These are assumptions made by a predictive algorithm. For example, in linear regression, the algorithm assumes that there is a linear relationship between the dependent variable and the independent variables. See on the right hand side, here we have one independent variable, that is x, and here one dependent variable, that is y. And this algorithm assumes that there is a linear relationship between this x and y. And due to this assumption, there will occur an error. And that error we call bias error or error due to bias. Some of the low bias algorithms are k nearest neighbor, support vector machines, and decision trees. Now, this list is not limited to 3. You have also high bias algorithms, for example, linear regression, LDA, that is linear discriminant analysis, and logistic regression. Now, what is variance? Variance is the amount of change in estimate by the learning algorithm L on changed training dataset. That means you have one training dataset and you have one learning algorithm L. You train that algorithm with this training dataset 1 and you get a model M1. Now you provide an input to this model M1, say the input is x, and this model estimate the value of this y value of this x as y1 hat. Now you take another training dataset 2, and which is not very much similar to dataset 1. You again use the same learning algorithm L, for example, say linear regression, and you train this algorithm and you get a model as M2. Now, you feed x to this M2 also, the same x, and you will get a corresponding y value, that is an estimation done by this M2 as y2 hat. Now, it is obvious that there will be a difference between this M1 and M2 because you have used two different kinds of training datasets, though you have used the same learning algorithm L. Now, due to this difference in this M1 and M2, this y1 hat will be somewhat different than this y2 hat. Now, this is the change in this estimated y we are talking about, right? Now, if this change is too large, that means y1 hat is very much dissimilar from y2 hat, then it will say that your model has overfitted. That means M1 has become too much specific to dataset 1, while M2 also has become too much specific to dataset 2. That is why there is a large difference between y1 hat and y2 hat, and we say the model has overfitted. And if the difference between this y1 hat and y2 hat is small, then you say that the model has underfitted. That means this M1 and M2 has generalized so much that when you change the training dataset, then also this y1 hat is very, very close to y2 hat. That means it cannot differentiate between this dataset 1 and dataset 2. And we say in this case that the model has underfitted. We have a small list of low variance algorithms here, that is linear regression, LDA, and logistic regression. In the previous slide, you found these 3 algorithms in the list of high bias algorithms, right? And on the other side, you say that this KNN, SVM, decision trees are in the list of high variance algorithms, but in the previous slide, they were in the list of low bias algorithms. So you can clearly see that whenever the bias goes up, the variance goes down, and whenever the variance goes up, then bias goes down. So you cannot have a model which is having a low bias as well as low variance. So during developing a model, you must have to balance between this bias and variance so that the model is optimized. So this tug of war between this bias and variance is called bias-variance trade-off. Next we go with coefficient of determination or R squared. This talks about the degree of variability in the target variable and that part of the variation that are explained by the independent variables. Now we go with the formula. R squared is actually explained variation out of the total variation, that is explained variation plus unexplained variation. That means this R squared is actually reporting you the proportion of the explained variation out of the total variation, right? Now what is explained variation? This explained variation is also known as target variation, and this variation is caused by the independent variables, what you have at present in the dataset. And the unexplained variation, it is that variation for which your present independent variables in your dataset are not responsible. Then what is unexplained variation? Unexplained variation is the variation due to the residuals. That means RSS, residual sum of squares. And how you find the residuals? You take the deviation of the true y, that means true value of yTV, minus y hat, that means estimated y, that is EV. You find the deviation between these two. For each y, you square those and add those squared deviations, and you get this RSS. And why it is unexplained variation? Because you do not have any control over this variation, because this variation will occur and the independent variables has nothing to do with this kind of variation. That is why we call this residual variation as unexplained variation. We also have a total variation like this. You take the deviation of TV, that is true value, from the mean, you square those deviations and add those, and you get TSS, that is total sum of squares. Then the explained variation will be TSS minus RSS, and the R square will be TSS minus RSS by TSS. Thus, R square will show you how much your independent variables are responsible for the variation in the target variable. Next, we go with zscore. This is also known as standard score, and it is a value whose unit of measurement is standard deviation from the mean. Say, for weight, we have kg as unit. For distance from a point, we have kilometers. Likewise, we have distance from the mean as SDs, that is standard deviation. Now, suppose we are going for an experiment with a few bags of rice, say, and we find that the mean weight of those bags is 145.2 kgs. Now, look at this scale. This scale talks about z-score or SD. That means this is a scale of standard deviation. The zero of standard deviation is in perfect alignment with the mu, that is mean of the raw score scale, because it is perfectly standing on the mu, right? Suppose we have a bag of rice with 175 kgs. Now, we want to find out what will be the corresponding standard deviation of this 175 kg in this scale. Now, it is obvious that the point will be somewhere here, which will be perfectly aligned with this point at 175, right? Now, we have to find out the amount of standard deviation from here to here. We go with this formula, that x minus mu by sigma. Now, this x is your observation data, that is 175. So, this is your observation data, 175. And this mu is the mean, that means 145.2. So, you find the deviation of this 175 from the mean. That means you are trying to find out the gap or the deviation between these 2 points, right? Naturally, we have to go for finding out the deviation between this point and this point, right? So you see that in the denominator, you find the value of sigma as 23.7. That means it is given like this, that value of sigma is 23.7. What is the meaning of this? It means that one standard deviation is equal to 23.7 kgs. So this relation will help you to find out the corresponding value in SDs. So if 23.7 kgs is equivalent to 1 SD, then what will be the corresponding SD for 175 kgs? So since 175 is not starting from 0, actually it is starting from mean. So you find out the gap of this deviation from the mean and divide it by 23.7 and you get 1.26 SDs. So here we go with the corresponding SD for this 175 kgs, right? Now, why we are doing this? Because for what we are going for this z-score? There are many applications of z-score. You can take the advantage. For one example, you can compare two scales. Suppose we have, say, for 23.7 kgs, and on the other side, you have 12 pounds. Now, these two records weights, right? This is in one scale and this is in another scale. So what you do is that you bring down this kg to a standard deviation. You bring down this pounds, this 12 pounds also in standard deviation. And now you can compare which one is heavier and which one is lighter. So this is one of the example application I talked about. There are many other applications you can find. Next, we go with maximum likelihood estimation, MLE in short. It's a probabilistic framework. That means this MLE works on probability theory. What it does, it finds out the values of parameters of a model for which the model has the best fit or optimized. That means, what are those values of parameters of that model for which the model has minimum error? That means, estimated y, for example, is very, very close to the true y. For example, you take normal distribution, and we know that normal distribution has two parameters. Number one is mean, and number two is standard deviation. Now look at this figure. For mean mu equal to 4.854 and standard deviation equal to 2.18, we have some kind of distribution like this. We have this shape. Now we keep the mean equal to 4.854, that is same mean, but we change this standard deviation to 1.07 from 2.18, and we see the shape has become narrower. In the third figure, you see that the mu has been changed from 4.854 to 3.54, but the standard deviation is 2.18, just like the first one. Now we see that the shape is somewhat looking like the first one, but the mean has shifted towards the left, right? Now you can clearly see that for different values of mu and sigma, you are getting different kinds of shapes. Now, when you have data, which mu and which sigma will be there for you so that your distribution is perfectly aligned, or not perfectly aligned actually, it is very, very near to the distribution of your data. So those values of mu and sigma are determined by this MLE. Now for one data point, that is xi, mind it, this is for one data point, the probability of one data point given mu and sigma will be like this, 1 by root over 2 pi sigma square, and this exponential part will be minus xi minus mu whole square by 2 sigma square. Now this part is actually the power raised to e. I repeat, this expression is actually the probability for one data point xi. Now we are interested in finding out the probability density function for all the data points xi's, and for that we multiply the probabilities of all xi's. This probability we call likelihood function. Next, we take log of this probability expression and we get this. And this log form is called log likelihood function. Now, why we are going for log? Because we have to go for step 1 as find out the derivative, and the second step is to equate that derivative to to 0 to find out the flat curve, right? Flat portion of the curve. And for finding out the derivative of this product will be somewhat difficult for us, right? For that, for an easier calculation, we are taking log so that it becomes a form in the summation form, and the derivative calculation will be much easier for us to calculate, right? After completing these two steps, you will find the corresponding mu and sigma square for which the error between these two will be minimum. Now, in this video, I am not going into details at how we have reached to this expression. I have a separate video on MLE where I have showed all steps to reach this expression. The expression for the mean will be like this: 1 by n summation of xi, and the expression of variance will be 1 by n summation of xi minus mu squared. Next, we go with Bayes' theorem. Before starting, you have to have the knowledge on joint probability, marginal probability, and conditional probability. We start with joint probability. This probability is dealing with two events, and both the events will occur simultaneously. For example, we have two random variables, genre and gender. Genre has three values, sci-fi, comedy, and war. Gender is having two values, male and female. And the total trial count will be 100. So we talk to 100 viewers. There are 10 persons who are males, as well as they like sci-fi movies. That means these two events are occurring simultaneously, males as well as sci-fi movies. For calculation of probabilities, you divide these data by 100 because you have 100 trial count, and you have the probability as 10 out of 100 for males as well as sci-fi movies. Marginal probability deals with one event, that is one random variable, irrespective of any other random variable present in the dataset. That means there may be more than one events occurring simultaneously, whatever it is, but we deal with only one variable at a time. For example, you say this 55. You are concentrating on males only, irrespective of this sci-fi, comedy, and war. On the other side, if you take this 25, then this 25 is actually talking about only sci-fi movies. So the last row where the totals are there, and in the last column will help you to get marginal probability. Clear? So the marginal probability of sci-fi movies will be 25 out of 100. Next, we go for conditional probability. Now, this probability also deals with two events. One event will occur first, and then the other event will occur. So, the conditional probability of event S, that means you are looking for sci-fi movie viewers, given M, meaning males. That means you collect male viewers in one place, and then you are trying to find out among those males who are those who like sci-fi movies. So, here the M event has occurred. After that, you are trying to find out the probability of the event S, that is sci-fi. So, it is written like this: P of S given M, and it will be 10 out of 55. In joint probability, this will be 10 out of 100 because both the events are occurring simultaneously. But here, you have got the event of males first, and for that, you have got 55. And out of those 55, how many are liking sci-fi movies? So, that is 10. And you clearly see that this 10 is actually the probability of S intersection M. That means the joint probability of S and M. And the denominator is probability of M. The conditional probability of event S given M can be written as, in the numerator you see, probability of M given S, that is the reverse conditional probability, times probability of S, and the denominator is probability of M as it was before. So we replace this numerator, it was a joint probability of S intersection M, it was like this. So this has been replaced with this expression in the numerator. Now when you go like this, that you are trying to find out the conditional probability with the help of the reverse conditional probability, we call it Bayes' theorem. Now if you find it a little bit clumsy, then you can make it flat. Take this P of M on the left hand side of this equal to sign, and you will get a pattern like say P of S given M times P of M, P of M given S times P of S. Now, when you will go for conditional probability, most of the time joint probability is challenging to calculate, and you have the reverse conditional probability in hand. Next, we go for Kolmogorov Smirnov goodness of fit test, kstest in short. It talks about how far your assumption regarding a population is correct. For example, you have a population of data and you do not know actually what is the distribution of this population. So it may be normal, it may be binomial, it may be Poisson, or any other distribution you may have. For example, say errors in linear regression. We generally assume that the errors in linear regression is having a normal distribution. We go for fairness of a coin. The coin has two possible outcomes, head and tail. For that, and if the coin is fair, so the probability of head and tail will be very near to each other, right? So for that, we assume that the distribution is following a binomial, right? So these are the assumptions regarding the data we have. Now, before proceeding further, a test is needed whether our assumption is regarding the type of the distribution is correct or not. kstest will say whether the data follows the assumed distribution or not. How it works? You find the deviation between S of x for all x's and the corresponding f0 of x for all x's, and you identify the maximum deviation between these two, and that we call d suffix n. This is a score of the kstest. Now, what is this S of x? S of x is a proportion of the sample observations. And what is f0 of x? It is the cumulative distribution function of assumed distribution, and that is probability of sample observation less than equal to x. So, S of x is a probability as well as f0 of x. Now, S of x is getting the probability from data, and f0 of x is getting the probability from the function defined, from the defined function. For example, if you have the assumed distribution as binomial, then the probability will be going like this: ncx p raised to x and 1 minus p raised to n minus x. So using this formula, you can find out the probabilities of individual x's in case of f0 of x, and from the data, counting the data, that is counting the frequencies, you can find out the S of x. Now, regarding this test, I also have a separate video where I have explained all the steps in details. Okay. After considering a sample data, we got this. Suppose the x is, this is for 0, this is for 1, this is for 2, this is for 3, and this is for 4. So there are 5 x's and they have their own frequencies. Now we find out the gap between these two, that is S of x for 0, that is S of 0. This one is actually S of 0, and this one is actually F suffix 0 of 0. This one is S of 1, and this one is F suffix 0 of 1, like that. So we find out the absolute deviations between these S of x and f0 of x for individual x values, and we identify that this is the maximum deviation, that is 0.0175. Now this value is appearing in two places, it doesn't matter. So we say that d suffix n is 0.0175. Next, we consult the KS table for d suffix n and alpha, and this alpha we took as 0.05, and we have this 0.068 from that table. So we have dn is this, and the critical value is this. Now we can clearly see that this dn is less than the critical value, so our assumed distribution is correct. Next, we go for confidence interval. Now, before going for confidence interval, you must have a clear idea about the normal distribution. This scale is regarding SD, that is deviation, standard deviation. We have learned already that the standard deviation 0 is actually the mean of the data, right? Now, if this is a normal distribution, the left-hand side of this line and right-hand side of this line both are symmetric. In that case, we are confident that 68% of the data will lie in this region between minus 0.99 SD and plus 0.99 SD. We are also sure that 95% of the data will lie between minus 1.96 SD and plus 1.96 SD. Again, 99.7% data will lie between minus 2.97 and plus 2.97, and also 99% of the data will lie between minus 2.58 and plus 2.58. Now, one thing to be noted that this percentage, this proportion of data are not affected by the shape of the distribution. Whether the shape of the distribution is higher, whether it is flatter, whether it is wider, it doesn't matter. Okay. Now, we are trying to estimate a population mean from a sample. Now, we take a sample count as 100. Now, sample mean is 79.1 meter. We also know that the sample SD is 7.6 meter. Now, we assume that our sample follows normal distribution. Then in that case, if you say that, well, we have the sample mean as 7.6 meter, then we can assume that the population mean is also 7.6 meters. But the point is, you are taking a sample and you do not know actually whether your sample is biased or not. You cannot have a point estimate like this, but you can say a range or some interval that I am sure that the population mean is exactly not 7.6 meter, but it lies between this and this. So that interval we want to find out. Now, regarding the interval also, you cannot be 100% sure that whatever the interval you are declaring, you are 100% sure that the interval is correct. That means the population mean will definitely lie within that interval. So in that case also, you must have some kind of amount of certainty. So in the question, you say that 95% certainty. That means they are asking you to get the interval of the population mean with 95% certainty. That means there is a 95% chance that you are correct, and there will be a 5% chance that your calculation may not be correct. So here we go with the raw score in meters. That means 79.1 meter is aligned with the 0 of standard deviation, and the formula goes like this: x bar plus minus 1.96. You have chosen this value. Why? Because you see here that 95% confidence is needed. And we know that in case of normal distribution, we are 95% sure that the data will lie between minus 1.96 SD and plus 1.96 SD. So these are the two values of SD between which 95% of the data will lie. That is the reason we have taken 1.96 over here. Now, this value is also multiplied by a standard error. You have only one sample in your hand. Based on one sample, it is very uncertain that whatever you are doing over here will be according to your requirement, right? If you have lots and lots of samples over there, and based on those so many samples, you are trying to find out the population mean, then that will have a reason, right? But at this moment, since you have only one sample, this should be penalized by the standard error. And the standard error will be 7.6 meter by root 100. That means your sample mean is by root over small n. And ultimately you get this, plus minus 1.49 meters. So it makes 77.61 meter on the left hand side and 80.59 meters on the right hand side. So we are 95% sure that the population mean will lie between these 2 points. Next, we go with ANOVA. It talks about whether the means of the populations are equal or not. So how it does? It takes the samples, it calculates the variances. There are two ways to go for the variances. One is within the samples, and the other one is between the samples. Based on these two variances, it says whether the means are equal or not. For example, see, we have sci-fi, comedy, and romantic. three groups of data, and we talked to 4 viewers each, and we got the score. And this x1 bar is the mean of these 4 scores. x2 bar is here and x3 bar is here. Now this f score is variance between divided by variance within. So this is a ratio. We have the null hypothesis as mu1 equal to mu2 equal to mu3. That means all the means are equal. Now we have to prove whether our assumption regarding the null hypothesis was correct or not. So how to calculate the variance within? Variance within means within the samples. So there are 3 samples. So for each sample, we go for the variation. So the first row, see, 89 minus the mean of the first sample. So this one is x1 bar, x1 bar, x1 bar, and this one x1 bar. So from x1 bar, you take the deviations and you square those deviations and add those squared deviations. So you get the variation for the first sample, first group psi phi. This one for the second group and this one for the third group. And you add all these variations and you get this 598.5. So this is variation, not variance. For calculation of the variance within, we have to divide this variation within by degree of freedom within. Degree of freedom for this one is 4 minus 1, that is 3. This one also 4 minus 1, that is 3. Here also 4 minus 1, that is 3. So 3 plus 3 plus 3 makes 9. So divide this 598.5 by 9 and you will get 66.5 as the variance within. Now we go with variance between. Now before variance between, first we go for variation between, and for that we need these 3 means. We do not need this data, we need the means only. And along with that, we need a grand mean. That means x1 bar plus x2 bar plus x3 bar. These will be added together and divided by 3, and this will give you grand mean, that is x bar, double bar. Okay? So this one is our grand mean. Okay? So you take the deviation between these means and the grand mean each time, and you will get the variation between. So you see 85.5, this one is the x1 bar, and this one is the grand mean, that is x double bar. You take the second one, x2 bar, and this one is the grand mean. This one is x3 bar, and this one is the grand mean. Now one thing you notice here that every time we are taking the squared deviations, we are multiplying that square deviation with the value of R1, that means the rows, the sample size. This deviation is called weighted squared deviation. So the weight here is the samples, the group size, the sample size. So here is 4, here is 4, and here is also 4. In this specific example, you have all the samples of same size. You may have different size, sample size, it doesn't matter. And you finally add these and you get 210.17. So variance between will be variation between what we have got over here divided by degree of freedom between. Now degree of freedom between is what? How many data are there? There are 3 data. So 3 minus 1 gives you 2. So divide this value with 2 and you will get this 105.09. And you get 1.58 as your F score. Now you have DOF between as 2, DOF within as 9. You have a significance level, say 0.1, and you look at the F table and you will find the critical value over there as 3.00645. Now our score is lesser than the critical value, so we do not reject the null hypothesis. Next we go for Poisson distribution. Now this distribution deals with occurrence count of events in a large population over a unit of time. That means it deals with intervals of time. For example, typo error count on each page. Now it may happen that say page number 2, page number 3 and page number 4 are having say 40 errors, and page number 5 onwards up to say page number 100 there are no errors. No errors. It may happen like that. So event will occur at random points of time. Well, if it is occurring at random points of time, but it deals with success and no success, right? So whether there is an error or not. If the error is there, we call it success, and if no error is there, we call it failure or no success. Now binomial distribution deals with success and no success, right? Then what is the difference between that distribution and this Poisson distribution? You see, in binomial distribution, success and no success are having almost equal importance. But say you toss a coin and you get a head or a tail, right? Now, if the coin is fair, then of course the probability will be 0.5 and 0.5. And if it is unfair, then it may happen like that, 0.7 and 0.3. Can a coin really, in real world, can a coin may have like this, that 0.9 as head and 0.1 as tail? It is too much biased, and performing an experiment which is so highly biased will not do good to your experiment outputs, right? But here we have a success and no success distribution like this, that it may happen that 0.001 like that with a success and no success 0.999. That is why binomial distribution will not do good in this kind of situation. So Poisson distribution will help you. So what we see, no definite trial count. That means n is tending to infinity. That means you have a lots and lots and lots of trial count to get some success. P of E2, say E2 is your error count, and probability of that is probability of success is very small, right? So P tends to 0. And if we multiply this n, the number of trials, with this P probability, then we get a finite and constant quantity, and that is denoted by this Greek letter lambda. The definition of this Poisson distribution goes like this, that if you go for this probability of this random variable x equal to this observation x, then it will be e raised to minus lambda dot lambda raised to x by x factorial if x is 0, 1, 2, 3, 4, 5 onwards, and your lambda must be positive. And if you do not fulfill this criteria, then you will get a probability 0. Let's take an example. We say a stenographer makes 1 typographical error per hour on average. Now, we want to find out the probability that the stenographer makes 4 typos or 4 typing errors in a given hour, say 6 p.m. to 7 p.m. So this per hour is an interval, right? So since it is an interval problem, and you can see that the probability of the error is very minimum, so we have lambda equal to 1, that is the average, and x is 4, and we have e raised to minus 1, 1 raised to 4 by 4 factorial according to this formula, and we get 2%. That means there is a 2% probability that the typist will do 4 errors in that interval. The last topic in this video is correlation coefficient. This is very, very important. Now, what correlation does? It studies the linear relationship between 2 or more variables. Mind it, it is studying the linear relationship, not non-linear, okay? So, if a change in the value of one variable is observed along with a change in the value of another variable, then these two variables are said to be correlated, or there is a correlation between these two variables. Say this side is having screen count and this side is ticket sales. Now you can see the dots over here, and we can see a trend line moving upwards when the value of x is growing larger and larger. That means whenever the screen count is getting higher, the ticket sales also goes high, right? And this we call perfect positive correlation. Why perfect? Because it is these data points are having a straight line. It is not like some data point is here, some here, some here, some here, some here, like that. Now, why positive? This x and y are moving in the same direction. See, this one, x is getting larger, but y is getting lesser. So we have a perfect negative correlation because x is moving in one direction while the y is moving in a different direction. And this is perfect because all the data points are lying on the same line. This is a positive correlation. because you have a trend from here to here, but this is not perfect because see the data points are scattered here and there, but there is a trend line going from this point and this point. Also, this side we have negative correlation, but the correlation is not perfect. In this data, we have zero correlation because no trend is observed through this scatter plot, right? Now, during correlation, you can say that x is related to y or y is related to x. The relation actually works both ways, okay? And one most important thing to be noted, correlation does not ensure presence of causal relation. Causal relation means x is a change in x is responsible for the change in y or vice versa. So this is not reflected in correlation. Correlation is just an observation whether there is a change in x corresponding to a change in y. Now we talk about coefficient of correlation, that is represented by small r, and it measures the intensity or degree of linear relationship between two variables. This is the formula for r, that is correlation of xy. It is on the numerator you have covariance between x and y, and in the denominator you have root over variance of x times variance of y. And this is the expansion of this term, covariance of y, that is 1 by n summation of xi minus x bar times yi minus y bar. And on the lower side, you have the variances, variance of x, that is this part, and the variance of y, that is this part. And you can have a simplification. You get rid of these y by n's, and this will do good for your calculation of r. Now, regarding r, we have 3 points to be noted. First one is, it is a number. Second, it has no unit. And the third, it lies between -1 and +1. I hope the video comes useful to you. If you have any question regarding the topics, you may write in the comment box. In the next video of this series, we will continue from topic number 21. That's all for now.